In the last video, we talked about what happens when we have the log of both the dependent and the independent variables in an equation. Now we're going to consider what we call semi-log models, where the log appears on only the left-hand side or the right-hand side of the equation. There are two types of semi-log models, which we'll call either linear log models or log linear models, depending on which side of the equation the log term occurs. A linear log model is one where the dependent variable is measured in levels of the variable, but one or more of the independent variables is expressed as a log relationship. In a log linear model, the dependent variable is measured in terms of the log of the variable, while the independent variables are all measured in terms of levels of the independent variables. In the case of a bivariate linear log model, if we plot the relationship between y and x directly, we'll observe a curve similar to that on the left-hand side of the screen, assuming that both beta 0 and beta 1 are positive. And what happens here is that a change in y is tied to the percent change in x. So as the level of x gets larger, the change in y becomes smaller in absolute terms. But if we plot the relationship between y and the log of x, as is done on the right-hand side of the screen, we'd expect to see a linear relationship between y and the log of x in the case of this linear log relationship. If we take this basic specification of the linear log model, the interpretation of the coefficients is that each of the slope coefficients is a measure of the change in y divided by the rate of change in x, or we can write that as the change in y divided by the percentage change in x over 100. So it's measuring the rate of change in x, but as a decimal, not as a percentage. Another way of putting it is that beta j is telling you how y changes when x is changing by a given percentage. This model would be appropriate if you believe that the change in the dependent variable that occurs is affected not by the change in the level of x, but by the percentage change in x. A log linear model is one that we tend to see quite a bit more. Assuming that beta 0 and beta 1 are both positive, a log linear model would look something like the relationship on the left. And if we graph the relationship between the log of y and the level of x, we'd expect to see a linear relationship. A log linear relationship is one where the log appears on only the left-hand side of the equation, and we see this in very many applications. In the specification, beta j is a measure of the percent change in y, actually the percent change in y over 100, that occurs when there's a 1 unit change in x. So we use this specification if a 1 unit increase in our independent variable results in a constant percentage change in the dependent variable. One common use of this is when we're estimating earnings equations to estimate the effect of an additional year of schooling or an additional year of work experience on an individual's income. Because what the coefficients would tell us is the percent change in income that occurs from an additional year of schooling. Except again, this is represented as a decimal rather than a percentage. So if you get a coefficient of 0.09, that's telling you that a 1 unit change in that variable would result in a 9% increase in earnings, or whatever you're measuring on the dependent variable. We use this relationship quite often when we have a variable that's growing at a constant rate of r. You may have seen in some other class this relationship, which tells you the value of a variable that's growing at a constant rate of r, and t is the time period here. A is the value of this variable at t equals 0, because when t equals 0, e to the rt would be e to the 0, or just 1. So this is essentially a type of exponential growth equation. And we expect to see this, for example, with populations. We might see this with many time series variables. We might expect to see, at least over some range of time, something growing at roughly a constant rate. To convert this into a linear form, we use the same strategy we've used before of taking the log of both sides. And the log of y is the log of ae to the rt. We know the log of the product is the sum of the logs. So it's the log of a plus the log of e to the rt. But because the exponential and the log functions are inverse functions, the log of e to the rt is just equal to rt. And when we add the error term into that relationship, we get a relationship where the log of the variable we're trying to explain is equal to beta 0 plus beta 1 times t plus an error term. So if you want to estimate the rate of growth of something that's growing over time, you would simply estimate an equation where you have the log of that variable as a dependent variable, you'd have a constant term, and you'd include what's called a simple time trend, where the time trend would equal 1 in the first period, 2 in the second period, 3 in the third period, and so forth for all of your observations. And when you estimate that relationship between the log of your variable and this time trend, the estimated coefficient multiplying time is just an estimate of the growth rate for something that's growing at a constant rate. So beta 1 serves as an estimate of that parameter r. This is where economists get estimates of the rate of growth of economic variables. So when you see measures saying that a population was growing at 3.2%, or that healthcare spending is growing by 5% a year, for example, the way in which economists get an estimate of that growth rate is exactly this way, where you take the log of the variable and you run a regression of that against time. The estimated value of beta 1 is nothing more than the growth rate of the variable y. This is an example that appeared in the textbook. If you looked at healthcare expenditures between 1960 and 2000, you had a growth rate that looks very much like the sort of exponential function we saw before. When we estimate a relationship between the log of healthcare expenditures and time, which in this case we just call year, we get this relationship. So the intercept of that was a negative 185.69, but the growth rate of that, or the estimated coefficient of 0.097, tells us that healthcare expenditures were growing by 9.7% each year. And you notice the r-squared for this relationship is 0.99, which suggests that healthcare expenditures really were growing at an exponential rate during this time period. Now, the reason we don't have more recent data there is some changes in the healthcare market slowed down the rate of growth after this period, particularly the growth of HMOs and other managed care type arrangements, so that the model would not fit quite as well in more recent years. Couple of things to remember. One is you can't use a log transformation on either a dependent or an independent variable if the values of that are 0 or negative. The log transformation is only going to be defined when we have values that are strictly non-negative. So if you have observations that are 0 or negative, a log transformation is simply not appropriate for your data. Another thing we should note in general is that when you select a functional form, you should select what type of model, whether it's a log linear, a double log model, or a linear log model, or some mix of a log model and quadratic or a reciprocal model, based on what economic theory tells us about the relationships among the variables, what prior studies have found, and also the knowledge you have of institutional features of the specific market. For example, if we're looking at the relationship between earnings and work experience, one thing we might expect is that the growth rate of earnings is not going to be linear. Early in a person's work life, earnings are likely to grow at a relatively rapid rate, but the rate of growth of earnings, or the percent growth in earnings, is likely to decline beyond that point. That suggests that the log of earnings is going to be a quadratic function of work experience. And in fact, this is one component of literally thousands of earnings equations that have been estimated since the 1970s. Keep all these factors in mind when you're trying to come up with a specification for the models that you're working with for your projects.